My name is Nick Connolly and I'm Chief Scientist at Datacor Software. I'll be talking about persistent data for secured containers. Is it a realizable vision? In this talk, I'll be covering some of the background to running containers at scale and looking at how data can be secured in this environment, at rest, in use, and in motion. I'll also be referencing a long-term research project that has the potential to improve software security. Firstly, let's look at how containers are run. In a typical environment, multiple applications access data through mount points provided by the host OS. The kernel implements the file system and the physical device drivers which talk to the underlying storage. As a result, the kernel, which has a relatively large attack surface, has unrestricted access to all of the data that passes through it. Outside of the kernel, access to data is controlled by regular file permissions or by access control lists. This works reasonably well, but there's a clear vulnerability if the protections can be bypassed or access can be obtained to the physical storage. In reality, the application environment is likely to be virtualized, and in the cloud, it'll be multi-tenanted as well. A virtual machine may even move between nodes whilst it's running. However, if the network between the nodes isn't adequately secured, this could expose sensitive information. A containerized environment includes a runtime and an orchestrator to schedule the containers. There are a variety of orchestrators that could be used, but in reality, Kubernetes is the de facto standard. It's effectively becoming the control plane for the enterprise, with operators defining the patterns of automation. Kubernetes nodes are usually provisioned as immutable infrastructure and are ephemeral. CSI drivers implement the container storage interface and provide access to persistent data. These are storage vendor specific. They consist of a CSI controller, which is responsible for coordinating storage requests within the cluster, and a CSI node plugin, which runs on every node as a privileged container. When an application is started, the node plugin creates mount points for persistent data. Access protections are implemented using C groups and namespaces. Note that the attack surface is larger when using Kubernetes because of the extra layers of software that have been introduced. For container native solutions, such as Datacor Bolt, the storage stack is containerized and is scheduled by Kubernetes. Kubernetes is typically deployed as a cluster, which may have thousands of nodes. And in a managed Kubernetes environment, such as AKS or EKS, the nodes are running on a multi-tenanted infrastructure. So, how do we secure data? There are three areas of concern: protecting the data when it's at rest, when it's in use, and when it's in motion. Let's start with data security at rest, because in many ways, it seems the simplest. Using an encrypted file system seems like a reasonable approach. It typically allows individual files or folders to be protected without imposing an overhead on the entire volume. The data is relatively secure on the physical storage, but this approach does have some drawbacks. For example, file names may still be visible, and that can disclose sensitive information. The encryption keys are usually associated with a user's account and can be vulnerable if a weak password is used or if administrative access is compromised on the system. There's also an overhead associated with the encryption that takes CPU cycles on the host. There are several potential sources of non-encrypted data with this approach. The swap space can contain in-clear data from the running processes. Nodes in a Kubernetes cluster are configured without swap space. Temporary files can unintentionally expose data that should be encrypted. For example, a work-in-progress copy of a file that is being edited. Log files can leak confidential information. And deleting an unencrypted file doesn't necessarily remove the contents. Free disk blocks can preserve data until they are reused. With an SSD for storage, this problem is worse because the data can be hidden in the over-provisioning area. An alternative approach is to use full disk encryption, such as BitLocker or PGP. All of the storage attached to the system, with the exception of a small region used during early stage booting, can be encrypted. This eliminates the risk of non-encrypted sources of data, but there is still an encryption overhead involved. The keys used in full disk encryption are stored in RAM and are therefore potentially vulnerable to cold boot attacks. Self-encrypting drives perform the encryption on the drive itself and can run at media speed. They also support crypto arrays where data can be securely deleted by destroying the key. They're a good choice, but there are vulnerabilities associated with the fact that the key is stored in the non-volatile media. The Keeper I/O proposal introduces much finer grained control and would enable crypto arrays for subsets of the disk. There is one significant difference between self-encrypting drives and full disk encryption. Data is transferred in clear across the interconnect between the disks and the host. Whether this matters in practice depends upon the connection technology in use, the sensitivity of the data, and the types of risk being protected against. In many environments, data will be stored on an array connected to a storage area network using NVMe over Fabric, Fiber Channel, or iSCSI. This improves capacity utilization and provides the opportunity for centralized data services, including encryption at rest. However, with the introduction of a network, consideration needs to be given to protecting the data in motion between the array and the server. With the advent of low latency NVMe over Fabric and the use of high performance Ethernet connections, it's possible to build pools of disaggregated storage where a remote disk performs to all intents and purposes as if it's connected to the local system. Note that the attack surface has increased significantly because there are now multiple systems with kernels and applications that can potentially gain access to the storage. There are also known vulnerabilities in RDMA, for example, the work on Nevermore, which is being covered in another session at this summit. In a Kubernetes environment, encryption at rest is enabled through a storage class. These are defined with a YAML file, and the exact syntax is specific to each storage provisioner. The example shown here is for EBS-based storage. Now that we've explored protecting the data at rest, let's consider data in use. In some ways, data is at its most vulnerable when it's unencrypted and being used by a process. The host OS has a relatively large attack surface, and any breach can potentially yield unrestricted access to the server's entire address space. To protect against this, secure enclaves can be used. Secure enclaves ensure that an application and its data are encrypted in memory and are only decrypted within the CPU at time of use. Attacks from the host OS privileged applications, other untrusted code, or even an underlying hypervisor will be unable to access the contents of the enclave. When the enclave is loaded, a cryptographic hash is calculated, which is used by remote attestation to verify that the application is secure. Enclaves can be used to run an individual application or an entire virtual machine. Secure enclaves are particularly relevant for sensitive data on multi-tenanted infrastructure. The Confidential Computing Consortium brings together hardware vendors, cloud providers, and software developers to accelerate the adoption of trusted execution environments. There's a range of hardware implementations. Intel Software Guard extensions isolate an application or a portion of the application. AMD's secure encrypted virtualization is designed to securely isolate an entire guest VM. It's supported by the major cloud providers. For example, Microsoft Azure has application enclaves to securely run an application, and confidential VMs to run an isolated VM with full disk encryption. Unfortunately, when we start talking about confidential containers, things become more complicated. The simplest approach is to add secure VM nodes to the Kubernetes cluster and run the sensitive workloads on them. For example, using Google's confidential GKE nodes. This is reasonably straightforward and provides a level of isolation from the underlying multi-tenanted platform. However, it does require trusting the kernel within the VM and Kubernetes. A more secure approach is to run sensitive containers in their own enclave, where they're protected from attack. This is supported on AKS confidential nodes. Enclave, which is a CNCF sandbox project, provides the container runtime to make this possible. Because the host operating system is untrusted, the services it provides need to be recreated inside the enclave using a library OS. A couple of examples of open source projects that implement a library OS are Oclum and Grameen. The library is designed to run a single application within a constrained environment, so it only needs to implement a subset of the kernel's functionality. So, we've got data encrypted at rest and a secure container running. That just leaves protecting the persistent data in motion. And for the purposes of this talk, we'll consider data to be in motion until it's been successfully transferred into a secured container. One of the most straightforward ways of securely accessing persistent data from an enclave is to connect directly to an object store like Datacore Swarm across the network. Provided that an encrypted connection is used, data will be transferred securely into the application. One disadvantage with this approach is the application needs to be designed to use an object store or modified accordingly. The library OS can be used to provide secure file access. For example, Oclum offers a read-only hashed file system for integrity protection, a writable encrypted file system for confidentiality protection, an untrusted host file system for data exchange with the host OS. This is a reasonable option, but ideally it would be possible to connect directly to block storage from inside a secured enclave. At the moment, there isn't really a good way to do that. The best option for future development may be to integrate a user space iSCSI or NVMe initiator into the library OS. SPDK is a well-regarded set of tools and libraries for writing high-performance, scalable, user-mode storage applications. It's cutting edge, leverages the latest NVMe features, and uses a poll mode algorithm with a lockless thread per core design. Work's ongoing to integrate TLS 1.3 support. It's production ready, portable, flexible, and open source with a permissive license. What's not to love about it? Integrating SPDK into the secure enclave may be a good route forward. In a Kubernetes environment with a container-native storage stack, it may one day be possible to build a system with both the client and the storage stack running in secure enclaves. This is starting to look like an interesting design, but is there anything we can do to improve the security of the data when it's inside the secure enclaves? There may be. We can start by using memory-safe programming languages such as Rust to reduce software vulnerabilities. Even further out, there's some very interesting security research being done. CHERI is a joint research project between SRI International and the University of Cambridge, which is revisiting fundamental design choices in hardware and software to dramatically improve system security. It's a hardware capability-based system which extends the CPU instruction set to enable fine-grained memory protection. Pointers have associated bounds and permissions, and invalid memory references will throw an exception. The long-term direction is towards software compartmentalization, with capabilities enforcing software isolation and also enabling granular and scalable data sharing. In time, this could lead to the creation of a new generation of storage stacks that are secured by design. It's not just academic research. ARM is leading a 5-year research program that launched in 2019 to define a new prototype security architecture based on CHERI. Morello is a research program to determine if the Morello prototype architecture is viable to create a more secure hardware architecture for processors of the future. A system-on-chip implementation of the architecture will provide a technology platform prototype, enabling industry and academic partners to test real-world use cases and inform future development. So, what can we conclude? Security is always a trade-off between the sensitivity of the data, the risk of it being compromised, the practicality of the solution, and the cost of implementation. In a containerized environment, securing data at rest is vendor-specific but straightforward. Securing data in use is achievable but has higher costs and is still in the early adopters phase. Securing data in motion is viable with an object store, but is still cutting edge for block storage. There's been a lot of progress, but there's clearly more that can be done. Hopefully you found the content interesting, and I look forward to hearing questions in the Slack channel, or you can reach me at nick.connolly@datacore.com. Thank you for listening.